All right. A big hello to everyone who's starting to roll in. Welcome to live Chegg Intro to Computer Science office hours. My name is Reese. I'm an instructional assistant at UC San Diego for the computer science department. And today I'm going to be helping with some tough computer science intro questions. So we're going to do some pointer practice problems and then some stack practice problems. And if you want me to cover anything else, make sure to drop that in the chat. All right, awesome. So I'll start with some pointer practice problems. And then again, if you want me to cover something else, we can switch gears and do something else. And then as I'm going, like you can drop in your major and where you're from. And if you have any questions and you want me to go over something again, then that would be great. So first off, given the following code, we're going to analyze what is the contents of P, right? So say we have this integer a, right? So the first line, we assign it to 10, and then oh, hi. So right now we're talking about C and pointers, but this is also applies to C++. It also can be applied to like how memory is managed in most languages. But I can give examples in C++ and C as I go. But right now this is just a practice problem with some C code. So a is going to be assigned to 10 as an integer. Sorry, my fingers get in the way, so I'm really sorry about that. Um, and then I like to draw it as a box. So I'm going to say the value of 10 is inside here, and we call this a. So every time we say a, we're referencing whatever is inside this box, whether it's 10, 15, whatever, but we know that it's 10 because we put it there. And then a has some address in memory, right? That's how the hardware knows like where it's going to be referencing. So you probably learned this in your classes, but it has some address. So I'm going to say like it's 123. So then what I do is and that's always how I go about solving these problems, right? Is I draw those boxes, I say the name, I say the address, just to make sure that I know what's happening. And then we say that star p will equal that, or p will equal the address of a, and it's the type of an integer pointer. So then p is going to equal whatever the address of a is, right? So therefore, we know that the contents of p, which is whatever's inside this box, is going to be 10, which equals a. Does that make sense? It's a little bit advanced to go through like pointers and C and stuff, but like like the introduction to pointers is usually there. But if you guys want me to backtrack a little bit and go through like the syntax of it, just let me know and drop it in the chat and I can switch gears. But here's that. So on to the next problem. So this is in C again. Say in C we declared this integer array with 4 integers in it, right? So when we do that, somewhere in memory, there's going to be the integers 5, 10, 15, and 20. So I start making boxes for them when I start solving these problems. Okay, I say that the number 5 is going to be there, the number 10 will be here, 15 here, and 20 here, right? So when we declare like integer arrays, that's really just like blocks of memory with the numbers in those blocks. So when we say that p equals array, right, we say that p points to 5 here. Okay, and then if we add 2 to p, right, then p will go down 2 lines, so go here, or 2 blocks. So here is p plus 2, right? So then we know that the contents of p plus 2 will be 15. And that's how I usually answer those types of questions. Additionally, we can further that question by saying, what is like the address of 15 here, or the address of array index 2? That's going to be the same thing as the pointer plus 2, right? So then we like index it and we can add to that pointer as we go down. So now let's just take a break from that and take a sec. And if anyone wants to like drop their major in the chat, or any classes that they're kind of stuck on, we also have office hours throughout the week. So if you're stuck with any of your classes, be sure to tune in to Chegg office hours. And again, for anyone who's still coming in, my name's Reese. I'm a computer science instructional assistant at UC San Diego, and I'll be here every week, Tuesday at 6:15, if you guys have any questions. And again, anything we don't get to today that you guys have questions about, I can go over. So that was another pointer question. And then for the next pointer question, do that instead. There we go. Okay, so again, I like to go really slow with these problems. I like to draw my boxes, write my addresses, and write the values. So I'm going to start out with my first box, right? We can call this A. And then we can put the value of 5 in it. And then what our program does next is it declares a pointer P, which is the type of an integer pointer, right? And we say P equals the address of A. So now what I do is you can then make another box, right? And we can call this P, right? Because every time we say P, that also has a value. So this will have the address of A in it. And then PP will be another pointer that points, that's an integer double pointer. So this double pointer points to P. So its value is the address of P, but it points to A, or it points to P and P points to A. So sorry, this is a typo. This wouldn't work. This would cause a syntax error because P is type integer pointer, right? So we can't dereference it twice because it only is one layer of pointer. So if we do that, like it'll cause a compilation error. But star P, if we just dereference that once, that will be 5. And star P, P will also be 5 because the double pointer PP will be pointing to the address of A, which points to 5. So then conversely, like dereferencing that double pointer will give you P. So I know that was kind of dense, and I can go over that again if you guys have questions about that. Or if you have a question on implementing pointers, I can do like a quick program and show you how to write it in either C++ or C. If you guys would find that helpful. Otherwise, I'll go on to this. Okay. So here's a memory layout, right? And I'm just gonna pause for a second, actually. And so anyone else rolling in, my name is Reese. I'm a computer science instructional assistant for UC San Diego, and we're here with Chegg doing live computer science office hours. So if you guys have any questions about your computer science classes, make sure to put those in the chat. And then to follow along, I'm just doing some pointer practice problems, and then later I'll be doing some stack practice problems, and then showing you some basic C++ coding. And that will correlate to those practice problems we've been doing. But if you want me to cover something different, also drop that in the chat and I can cover that. Okay. So here's another memory layout. It'll have the variable name, the address, and the value. So this is just like those boxes I was drawing. I'm gonna make my pen a little bit smaller so we have a little bit more space. Okay. Um, Hello. It looks like the window's frozen. Okay, well, for some reason, my notebook isn't working, but while I try and fix that, oh, okay, it's back. It's not frozen anymore. Let's see if I draw. Okay, now I can draw. This is a lot for my poor little old iPad. It's time to upgrade. Okay, so once we have A, we'll give it the value 10 and the address of OX1000. We'll have the variable B with the value of 20 and the value of OX1004. And then I'm just going to move over here. So we have the box with the name of pointer A and the value of OX1000. So this one has the value of OX1000, which we can see over here is actually the same address as A. So we'll keep that in mind for later. And then pointer A's address is 1008. So we already know that pointer A points to A. And then pointer B has the value of OX1004, and that one will have the address OX1000C. And again, we can notice that 1004 is the same as B's address. So we know that pointer B points to B. All right, so knowing all that, now we can follow this code down here. Okay, so the first line is saying that the contents of pointer A equal the contents of pointer B. So when we say contents with this start right here, right, that means we're not saying what's inside the box, but we're saying what's inside the box it's pointing to. So let's see, let's follow it. So pointer A is pointing to A. So we're going to change the contents of pointer A to be what pointer B is pointing to, which is 20. We're just going to change that value to 20. And then here, we're changing the value of pointer B to be pointer A. So we didn't dereference it, which means we're not going to a different box. We're staying in the same box, so the same value, which means that this value will now be OX1000, because again, pointer A is OX1000, right? And we're changing pointer B to have the same value as pointer A. So now, because pointer B has the same value as the address of A, pointer B doesn't point to B anymore. It points to A. And now we're saying the contents of pointer B equal 50. So we dereference pointer B, so we go from here over to the box and we say What's inside this box will be 50. So after we run all that code, the things that changed were that A became 50 and pointer B now has the same value as pointer A. And now nothing points to B. So taking a sec from that, if you guys had any questions about all that, you have more pointer questions, be sure to drop those in the chat. If you guys have any questions about anything else, this is Chegg Intro to Computer Science office hours. So if you're rolling in, just say where you're from, how you're doing, and just any questions you might have, you can put those in. Next, I'm going to cover some stack frame practice problems, but if you want to go over what I just did or have any other questions, you can go over what I just did because these will all be recorded on YouTube. So you can go back and watch this and follow what I went through. Or if you want me to do another example, just make sure to ask and I can do a different example. Okay. So here's a stack frame practice problem. Okay. So given this code, we're going to draw the stack frame. Okay. So when any function invokes, when any like program runs, it always runs with main in C, right? So here's our main function, and we're going to start with that. So we're going to draw main stack frame first. So main, after it returns, it's going to return somewhere. We don't know and we don't care where it's going to return to, but it has some return address that it's going to go to. So that's just like return from main. Okay. And then the next thing that main does is it declares a local variable called num. So then it puts that on the stack. So this is num. It has the value 5, and num is the size of 4 bytes because it's an integer. So this is 4 bytes long, and the return address, because it's a pointer, is also going to be 4 bytes. So that's our stack right now. And then the next thing main does is it calls function A with the parameter of 5, which is num. So now we go into function A. So when A gets called, the first thing that function A does is it writes its return address on the stack. So it returns to main. And if we called this like line 1, we know it would return to line 1. Okay. Then the next thing that function A does is it declares another local variable called A. So this is A, right? And, oh, sorry, my bad. Before it does that is it makes a copy of what it was passed into. So it has its own copy and it calls it X. So X is going to be 5 because it's equal to num, but it's passed by values. So when things are passed, right, it makes a new copy. So func A has this other value of 5 and it references it as X. And then it makes its local variable A, which is X plus 1, which is 6. And all of these are 4 bytes because they're all integers. Yeah, good question from Boomshroom. The return value for main, there is a point to that. So when you call a function, right, you want it to return to like the system, right? Like you run it from your terminal and you say run this program. Main needs to return from that into like the system, into the terminal, so that it doesn't just get stuck in main, like the program counter. If that makes sense. Like main needs somewhere, the program knows where it needs to know where it needs to go after main returns, like to know to go back to the terminal to like do something after main returns from, because maybe it was something else that called this file that had an invoke. Like however we called it, more things will happen afterwards. So we always need to know where we return from main. Okay. So A will be x plus 1, and that'll be on the stack. And then the next thing func A does is calls function B with the parameter of 6. So now we're in function B. So this is function B's stack frame. And then this will return to function A. And if we call this just like line 5, I'm just giving them random numbers so that we can say where it's going to return back to. Actually, it wouldn't return to this line. It would return to the line right after. So here. Same with this one. It would return to this line right here so that it knows that that's the next line to run. So from Nick on TikTok, I think what you're asking is I think what you're asking is where it goes to run the functions. And yeah, that's a good question. So it doesn't matter where it is in the code. It could be at the beginning, it could be at the end. Like in your code, whatever address function A is at, it will run it from there. So when it calls function A, wherever function A is at, the line within function A, the start of function A, will start running. Does that make sense? Or do you need more clarification on that? Okay. And then before I finish the stack frame, for more people rolling in, we're doing stack frame practice problems. I did some pointer practice problems earlier, so if you guys want to check that out after the live stream, you can see what I went through. And if you want me to do more pointer practice problems, I can do that. Or if you have any questions about anything else computer science related, we can switch gears and work on that. But now I'm going to finish function. I'm on function B. Function B is stack frame. So these are the stack frames just relative to each function. So this is like the entire stack frame, right? Like that runs when we call main. But right here is main stack frame. Like if main said print x, which is here, the program wouldn't know what to do, right? Because x is not within main stack frame. X is within a stack frame. So it matters what function the stack frame belongs to. Okay, so now we're on function B stack frame. So this is B. We return to function A, and then we have a copy of the parameter, which is called y, and that equals 6. And then the next thing that B does is it creates a new integer called B, which is y times 2, so that's going to be 12. And then it calls function C. And at this point, I'm running out of space for my stack frame. So let's see if I can, I'm just going to move it over here. Okay. Oh, no. Okay. So now that we call function C, same thing. We want to have the return address back to function A. Or sorry, back to function B, the caller. We always want it to return back to its caller. And we have a copy of the, so I'm going to continue up there. We have a copy of the parameter, and it's called z. So z equals 12. And then function c creates a new integer called c, and that's z minus 3, which is going to be 9. Okay, now that function C is returning, the stack starts to unroll. So once it returns, all of the function C stack gets popped off the stack. So we added this last, so that gets popped off first because it's like a stack. What you put on last gets popped off first. And then once this return is popped off, then our program counters back to right here. So we had the return address that told us to go back to here. It said, go back here. And we're like, okay, we'll go back there. And then the next thing that runs right after it is it returns, right? So then we pop everything back off the stack. So B gets popped off, Y gets popped off, and then we return to function A. So where we left off in function A, the return address of function B was here. So now our program counter's there. And then the next line of code that happens is function A returns. So now we're in function A, and because function A is returning, everything gets rolled off that stack. So we get rid of 6, we get rid of 5, and then we return to main. So that's right here. And then the next thing that happens is main returns 0. So we take everything off of main stack, and main returns to wherever called it. We don't know and we don't care, but it just stores that in there so it knows where to go next. Yeah. Did that make sense? Or does anyone have any questions about the stack frame overall? The stack frame also grows downwards, so so when I do it, there are higher memory addresses up here and lower down here. In case sometimes in your classes you need to label the addresses, it says start from these addresses or what's on this address, and like then you can do it by address and really track where everything's going. Okay, and then here's another stack frame practice problem, but I'm just gonna pause for 1 second and see if anyone else has any questions, if there's anything else you want me to go over, or there's a different topic you want, or anyone else just rolling in. I'm Reese. I'm doing Intro to Computer Science office hours online with Chegg. And if you want help with a different subject other than computer science, we have office hours throughout the week. You can scan the QR code and just look at our schedule and then tune into those. And if I don't get to everything you wanted me to cover today, you can tune in next week. I'm here on Tuesdays at 6:15 Pacific time, so you can come by next week. So Ken from TikTok asked what language. So this is C, but it's also pretty much the equivalent C++, but it's just like the stack frame. But the stack frame any language, so this like shows how when any language runs, the stack frame starts building and you can follow it along. But if there's a specific language you want examples of, I can show that. And Nick on TikTok is referencing this. So Nick is asking, what does void func tell the computer to do? And I think to answer that question, correct me if I'm not answering it, but void func, void is the return type. So that means it returns nothing. It just runs and then returns. And in these cases here, they don't really do anything for the purpose of the program, right? It just runs and then gets rid of the things it just stored into the stack, but it is really helpful for drawing out the stack. But say like these all returned integers instead of void, we could say return func B, and that way whatever func B returns, func A will return. And so the functions like all get called to collaborate on a final return value. So if we like return C here, and then return func C with parameter B, and then return func B, and then if we finally get it in main, then func A will have a value that's an integer. But basically, void is the return type, which means it's not returning anything at all. And func A, that's just the name of the function. It could be called anything. It's like a variable name. So when you call it, it means that code will run wherever it is. So when we say func A, that just means that this is going to run with num as its parameter, so num being x. And I can do another problem and show that, especially with different return types, if that would be helpful. Maybe this will be helpful too. This recursive function stack frame. Does anyone have any languages that they want to see? Or does anyone want to tell me where they're from, how they're doing? Just drop anything in the chat. And okay, so if we draw the stack frame again, we start out by calling main, and main always returns an integer. So again, int's the return type, and void up here means it doesn't return anything. But what we can do instead is I'll change the void return type to be an integer instead. So we'll say it'll return an int, and then it's actually going to return this. And then we can say print this. And this isn't the correct syntax for printing in C, but just for the cases of right now, we're going to just say that prints to like standard out. Okay, so when main calls recursive function with the parameter of 3, right? The first thing that happens is we have the return address of main. Okay. And then main calls recursive func 3. And because main didn't assign 3 to its own local variable, like int x equals 3, we don't put 3 on the stack. That's just passed right into recursive func. So when recursive func is called, that's its stack frame. 3 is passed in, right? So we're going to say n equals 3. Okay. So the first line runs, if n equals 0, then recursive func returns, and it's not, so we keep going. And then it declares its own local variable x. So we say int x equals n times 2. So x equals 6. Oh, and we also have to do a return value here because it needs to now, so we need to have a return value. I'm also going to modify this a little bit to see how our code changes. So instead of it being return recursive func, I'm going to say it's return recursive plus n. Okay. Now you can keep going with your stack frame. So x is 6, and then the next thing that happens is our return value is going to be whatever returns plus n, but we need to call this function in order to do that, right? So we call it here, and then this is going to be the line that returns to. Okay. Or we'll do plus x so that x actually does something instead of just computing it. Plus x. Okay. All right, then we're calling it the same function that we're inside of, which is what makes it recursive, right? So we call a recursive func again, right? And this new iteration of recursive func is passed n-1, which is 2. But in this iteration, it makes a new copy of n for itself. So it says n equals 2. And then starts here. So if n equals 0, return, which it doesn't, and then x equals n times 2, which is 4. So x equals 4. And then it calls recursive func with the value 1. So here, I can label these also. Maybe that will help us track these. So this will be recursive func with the parameter 3. This is recursive func with the parameter 2. And now we're calling recursive func again with the power of 1, with the parameter of 1. And none of these are rolled off the stack yet, right? Because none of the functions have returned yet. So all of these are still on the stack. Okay. I'm gonna get a new color so we can keep tracking it. Okay. So recursive func with the parameter of 1 makes its new parameter a copy of the parameter and says n equals 1. And if n equals 0, then it returns, but it's not. Then we go to the next line, and x is 2, so x equals 2. And do you see how like there are all these values of x, but they have different values? That's why each function call has its own portion of the stack, because they're all called x, but they all have different values and they all like are stored in there. Okay, then it calls recursive func again for hopefully the last time, and then we can put everything together. So n minus 1 is 0, so we're going to call func the parameter of 0. Okay. And then our first line is if n equals 0. Oh, I'm so sorry. All of these need return addresses. I totally forgot to add those in. But all of these will need return addresses so they know where to return back to. I'll just add those to the tops of the stacks. And they all return to the same line in the code, right? They all are returning to right here. So the program counter doesn't, it's the same line that it keeps returning to. It uses what's on the stack, right? So later. And then we have a return value here. So now that we can find a stack, recursive func return 0. So we can take this bottom function off the stack, and where do we return? We return to here. So recursive func with the parameter 1 called the same thing with the parameter of 0, right? And that returns 0. So what does recursive func 1 return? It returns 0 plus its version of x, which is 2. Okay? So I can track that somewhere. I'll put it up here. So recursive func was 0. Recursive func 1, func, the parenthesis is 0 plus 2, which equals 2. And now recursive func 1 returns to the exact same line, but with a different stack frame. So we again are still on this line, but our stack frame's different, and we have a new return value. So this returned 2, right? And then we have the value of x being 4. So now we return 2 plus 4 for recursive func with the parameter 2. A little table up here, and I'm just gonna do that so I don't keep writing it out. With the parameter 2 is gonna be 2 plus 4, which equals 6. And now we can pop, 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 pop. And we return to the same place, just a different stack now. And this was called with the parameter of 3. So finally, recursive func3, which remember was called by main, so it returns a different place, equals 6 plus 6, which equals 12. So recursive func3 returns 12. So when we go back here to main, now we can print it out. So main prints 12. And then, because we return from this, we pop all this off the stack. And then main returns 0 to wherever that called it. Okay, so recursive functions are really heavy and a lot. And sometimes it's really hard to keep track of everything, especially when there's computational depth to map it out. Like if we even had like 5 iteration, I probably would have I might have already gotten lost. So part of your job is to keep me in check and make sure I don't. So if I make a mistake, make sure to drop that in the chat. But yeah, so it's really hard to track that throughout the frame. So it's really important that you draw out everything. You make a lot of notes and you're organized when you track it through. Another way to solve this, if without drawing the stack frame, if you were just asked by your teacher, like, print recursive func3, what you would do, or what I would do, is I would say recursive func3. Oh no. I'll write it again, but I'll add a new page. Recursive func3. And then when it calls itself again, right, that returns recursive func2 plus x, which we already computed x, right? So we already knew that it was 6. And then what we can do is write it again. Oh no. Sorry, sometimes it gets really confused whether I'm doing stuff with my mouse or with my Apple Pencil, so I need to recalibrate that. So then we can say recursive func2 equals the same thing with the parameter 1 plus, what was the value up here? It was 4. And then same thing, but with the parameter 1. That was the same thing, but with a parameter 0 plus 2. And then recursive func0 was 0. So now we can fill those in. So we can say this is 0, which equals 2. This is 2, and that equals 6. And then 6 plus 6 equals 12. And that's another way to do it that I find a little bit easier, but sometimes when you're learning the stack frame, you have to draw it out, and it just takes a little while. But you can always check yourself by doing it this way. And then another great question from TikTok is how can you tell if something's recursive in assembly? If any of you are classes, but master stuff like this, like pointers and stack frame, you move on to assembly, and there's a couple different types of assembly. There's like ARM assembly and there's x86. If you're working on assembly, you should tell me in the chat and what you're using. But how to tell if something's recursive in assembly is, when I do it, is it's hard to do it without actually running the code and tracing it completely. But it's usually if the same function is called, it's when the same function is called within the function. So most assembly, or like ARM assembly, will have a function, right? So like we'll say it's like some function foo, and if at some point in the code, like dot 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 dot, if it calls foo, which is done by BL, that's how you call a function in assembly, in ARM assembly, then we know it's recursive, right? Because it calls the same function within the function. The tricky part about other versions of assembly is it doesn't actually say the name of the function sometimes. Sometimes it just says the address. So an equivalent would be like if foo was at address 0x034 or something. Sometimes it says BL 0x034, right? And that would be the same thing, but that's a little bit harder to track. But in the end, if a function calls itself, then it's recursive. From Dre on TikTok asked if I already went through the Fibonacci sequence, and I haven't. So we can do that now and map that out. I'll just start by writing it out, and then if we want to go through and trace the stack, or just trace the return values. x86. So for x86, I think it's something similar. It's not this exact syntax, but I think you will see the function being called within the function. And if you guys want more assembly covered, I can totally do that. Just let me know and maybe tune in next week and I can go over some assembly. And right now I'm going to do the Fibonacci sequence. So if you guys aren't familiar with the Fibonacci sequence, it's where you start with a sequence of numbers that add the previous two numbers. So it goes 0, 0, and 1. Or maybe it's 0. I don't particularly remember. And then 0 plus 1, and then 1 plus 1 is 2, and then 3 is 5. 3 plus, and so on. So how we would do the Fibonacci sequence is pass in order, just like what Fibonacci sequence you want to do. And you just pass in like an index or something. So if we passed in like 4, we do 0 and so 3, 2, 3, 4, and 3. So what we would do is we would check, we need a base case. So if I is or equal to 1, so if it's 1, 0, or no, our base case is here. We would want to do 0. If I equals 0, then we 0. And then if I equals, we return 1. So actually you could do that when I is less than or equal to 1, then you return I. And then what you would do is you would return the sums of I minus 1 plus Fibonacci of I minus 2. And then recursively, it'll add up all those numbers and form your return value in the sequence. If you guys want me to go over that stack frame, you can. I just did a bunch of stack frame things, but I can definitely do that. Or if you want to just rewatch that stack frame, do that on YouTube. This will be recorded after. If you want to tune in next week, I'll be here at the same time and we can cover. So I think a couple people are talking about digital logic and signals and systems. I think that goes over a little bit of the scope of this in science, but if you want logic and systems, then we can try and cover that if we have a little bit of time. So I'm not gonna trace the stack for Fibonacci, but I'm just going to, and if anyone's just tuning in, we're doing Intro to Computer Science office hours, presented by Chegg. And I've gone over pointers and stack frame practice problems. And if you guys want to review those, this will be recorded after, and I'll be here at the same time next week because we're almost out of time, unfortunately. And if you guys want any help with any of your other subjects, the QR code's up there, and just scan that. You'll see the schedule. And if you guys want any other help, like outside of office hours, be sure to go 4/7 with help. So if we wanted to do Fibonacci of index 4, we'll just do it 4 times. I does 1 equal 0, turn Fibonacci of I minus 1 plus I minus 2. So Fibonacci of 3 plus Fibonacci of 2. Okay. So Fibonacci equal to 1 or 0. So we do Fibonacci plus Fibonacci of 1. And then Fib 2, same thing up here. So I is not equal to 1, it's not equal to 0, so it returns Fib 1 and Fib 0. Okay, we've arrived at our base cases. And these are super important when programming recursive functions, because if you don't have base cases, then your function's going to run forever, keep calling and calling and calling itself, and it will never stop and never return. 1 returns 1. And Fib 0 returns 0. So then we can start subbing these in. 2 is going to be 1 plus 0, which equals 1. Fib 3 is going to be 1 plus 1, which equals 2. And Fib 4 is going to be 2 plus 1, which equals 3. So then if we go back up to our 4th index, it does equal 3. That's awesome. But yeah, no, recursive functions get really chunky. So just writing it out just like that is the most helpful for me. Do you guys have any questions on stack frames or want me to go over any more pointer practice problems? Or if, as we're wrapping up, do you guys just want to say like what you're majoring in, where you're from, and like what's the hardest subjects you're going through right now? And what topics in like computer science you're most interested in? And if you didn't realize, I'm an instructional assistant at UC San Diego, and I perfect problem. And hopefully you guys agree with me. I can make this a little bit easier and more of these tricky concepts. So to wrap things up, I'm gonna do 1 or 2 more pointer practice problems. So, and some people are asking about assembly. I can do, if someone would prefer, I can do a pointer practice problem in assembly. Just or a different topic, just for one more problem as well. But for right now, let's see. So I'm gonna say I have an int x and that equals 50. And I'm gonna have an integer pointer p that equals x. And then I'm gonna declare an array. And that'll be of size 3. And that has 1, 5, and 20 in it. So if I draw this out, we have x here with the value of 50 and p with the value of the address of x, and then our array, which has a bunch of integers in it. So if we assign p to instead be the address of array 1, if we break that down, array 1 is going to be 5, right? So p will now be this address of array 1, and I'm actually going to give it a number just to make it a little bit easier. So we're going to start at 100 here. This will be 104, or yeah, 104 because integers are 4 bytes, so we need a 4-byte block to store these integers. So this will be 108, and then p will have the value of 0x104. And then if we do like p++, so we increment p, and then say maybe like the contents of p equals x, then what that is going to do is p gets incremented, and sometimes your teachers are just like, or your professors are just going to want you to like trace these problems and write things out, and I just always like to draw it out because, you know, doing it in your head with enough practice will work, but when you're first learning, I like drawing it out. It's just the easiest way to visualize it too. So P is going to be 108 because in C or any other language, any other higher level language than like assembly, it does pointer arithmetic for you. So when we add 1 to it, because it's a size int, it will add 4 to it. So then it will now be 108. And then if we say star P, so dereference P, which is this, and then we say it's equal to x, that will be the equivalent of saying array at index 2 equals x. That's 20, but now it gets changed to 50, which is the value of x. So that's kind of like a high-level view of how things get changed around in memory, how you would track them, and just like how you could manipulate memory with pointers. And yeah, again, like if you need help with anything else, I think someone had a question on derivatives or math and stuff, just be sure to scan that QR code and then you can see the schedule of the hours throughout the week. We have a bunch of different subjects for online office hours. And if you want to do more computer science office hours, I'll be here next Tuesday at 6:15 Pacific time. So yeah, just tune in there. And as we're wrapping up, remember that if you want some 24/7 help, just go to chegg.com and we have a bunch of resources there. And make sure to follow Chegg on Twitch, TikTok, Instagram, YouTube. And if you need more homework help, you can go in the chat and use the code CheggLive50 for 50% off your first month. So be sure to claim that because that's a really good deal. If anyone else has anything you want me to cover next week, now's the time to put that in the chat. So, thanks everyone for joining. And next week, I'll cover some similar things and maybe some more coding in C++ and C. And if there's more questions about digital logic, then I will prepare some of those in case there are more requests for those. Even if it's a little bit out of the scope for intro to computer science, but if there are requests for those, I'll prepare some questions for that. But yeah. And again, I'm Reese. I go to UCSD and I'm an instructional assistant, and I'm really grateful for you guys coming in and joining the live.